Alright you guys, this is video E3.2-1. These are notes on section 1 inside the Earth, and we're looking at the learning target of E3.2a. Describe the interior of the Earth in terms of crust, mantle, and inner and outer cores, and where the magnetic field of Earth is generated. So we should be looking at this set of notes here. I'm going to move over to the PowerPoint. Get this going here. Alright. So, section 1 inside the Earth. Scientists think about the physical layers of Earth in two ways. One, by their composition, what they're made of. So in parentheses, put what they're made of if you need to. And two, by their physical properties. We have one set of names based on what they're made of, and then another set of names for all the layers of the Earth based on their physical properties. Now let me remind you as we go through these notes, in some sections you're going to be writing more than in other sections. Please go ahead and pause this if you need to. So number 2, what are the three layers of Earth? From least dense to most dense. We have crust, mantle, core, and you can see in this diagram here the relative sizes or thicknesses of each of these as we work down. Mantle, and then the core is divided into the outer core and inner core. Please note, the outer core, metallic liquid, that's very important. We'll get back to that in a moment. 3, what's the outermost layer of the Earth and how thick is it? We're talking about the crust here, and it's anywhere from 5 to 100 kilometers thick. It's brittle. Most earthquakes are occurring here, and in this particular diagram I have it showing continental and oceanic crust. That is our third learning target that we're going to talk about, C, a little bit later, so we will come back to this diagram here as well. And again here, two types of crust, continental and oceanic. And don't look at the water here, but look at the crust underneath it. And it really does look like it's compressed. It's more dense than that continental crust. Have we ever drilled through the crust to the mantle? The answer is no, absolutely not. That's 5 kilometers to 100 kilometers thick. So we're talking about like 3 to 60 miles thick. But we do have volcanic vents, like we're seeing in this picture here, that are cracks in the crust that allow this molten rock to escape onto the surface. Which layer of Earth accounts for most of Earth's mass? Well, it is the mantle. You might be inclined to say maybe the outer core or something like that, but if we look at all this space here that the mantle's taking up, and then think about the fact that it goes all the way around here, that is most of Earth's mass. So now we're going to talk about the physical layers, and this is where I think you're going to be writing some more, so please pause this as you need to write down this information. I believe we're going to be looking at the same diagram here. So first off, the lithosphere. Outermost rigid layer of Earth has two parts, the crust and this upper mantle, the rigid upper mantle. And it is the lithosphere that is divided into our tectonic plates. The asthenosphere is the next piece. It's a plastic or putty-like layer of the mantle on which pieces of lithosphere move. So the tectonic plates, the lithosphere, is floating on this asthenosphere, and we say it's plastic or putty-like because it's not exactly solid rock. It's kind of a magma. It's in between, and it flows. Beneath the asthenosphere, we have the strong lower part of the mantle called the mesosphere. Meso means middle. And then we have the outer core, liquid layer of Earth's core located just below the mantle. And then finally the inner core, thought to be mostly iron. It's very, very dense under a lot of pressure. This is where Earth gets much of its heat. Solid, dense center of the planet. So hey, what are the tectonic plates? Well, we've already kind of said they're the piece of lithosphere that move on top of the asthenosphere. And in this diagram with all this color, we can see the different plates. Now you saw previously a map that had all of the earthquake data, and it outlined all these plates. Here's North America right here. We are in Michigan, sort of right in the middle of this North American plate, the brown one here. Okay, and right here, if you follow my cursor, is that Mid-Atlantic Ridge. So 9, how is a lithosphere like a jigsaw puzzle? Whoops. Well, they're all fitting together like pieces of the puzzle. We addressed that really when we talked about the South American plate and the African plate here, and how these these two continents seem like they could have been together. Explain how tectonic plates float on the asthenosphere. My explanation down here is, as we look at this diagram, we have the green continental crust, the purple oceanic crust, and then this rigid upper mantle, which is part of the lithosphere. We see our arrow here signifying that. And it's floating on this red portion, the asthenosphere, and it says plastic asthenosphere. Plastic as in it can flow, it can move. So I say just like ice cubes in the glass displace water, tectonic plates are going to displace the asthenosphere. And I say think of icebergs, because if we're looking at this, the laws of buoyancy tell us that objects floating in water are going to displace it at this rate, especially when we're talking about ice. This is really what an iceberg would look like, in that only this small portion is going to be viewable above, and this very large portion is beneath. So we think about that and how much water that may be displacing. Come back to this and think about what our crust or our lithosphere is displacing. Okay, remember they're moving because of these convection currents that would be happening down here. Right? These convection cells of warm rock rising and cool rock falling. We'll get to that a little bit later as well. So how do scientists know about the deepest parts of Earth? Simply because of earthquakes. Seismic waves travel at different speeds through the Earth. Different seismic waves travel at different speeds through the Earth. And the speed depends on the density and composition of the material. In other words, what the material is made of. So we have all these little people here on this diagram of the Earth. The purple going through here are S waves, or secondary waves, and the P waves are, I'll call that blue. It might look more purple to you, but they're primary waves. Primary means first. They're going to get there first because they're the fastest, and they can go through anything. Okay, so if this point right here on the left is our epicenter, or our focus, it's going to move through Earth. It can go anything, goes all over. But notice how instead of just shooting right up to the top here, where it's moving through the outer core, it goes slower. Remember, our outer core is a metallic liquid. Okay, things move slower through liquids because the molecules aren't as closely packed together. So our S waves never get through the center of Earth because of this outer core, this liquid layer. Right? So we learned a lot about the interior of Earth based on earthquakes, and when S waves, say, would not arrive at a point here, or here, 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 all these places on the right-hand side of the diagram, those S waves never got there because of this liquid layer. We know that S waves cannot travel through liquids. So we've kind of touched on this already, but the outer core is the part of Earth that is molten. We think it's a nickel-iron alloy, which just means a combination, really. And we believe that this controls the Earth's magnetic field. The movement of this liquid, or flowing of this metallic liquid, controls the Earth's magnetic field. And as we were talking about those seismic waves, the denser the material, the faster the wave is going to travel through it. So whether we're talking about a sound wave or anything, the denser it is, the faster the wave travels through it. Solids are more dense than liquids, liquids more dense than gases. So a P wave is going to travel very quickly through a solid. But when it hits a liquid, remember the P wave will still go through it. P wave is still going to go through it, but instead of flying through it here, we've hit this liquid and we're going to slow down to go through it. And then we get out of the liquid and we speed back up. Okay, we can talk more about this diagram down the road as well. Hey, and that's the end of our notes here.